Okay guys, let's take a look at Leetcode 403 frog jump. So like usual in my past couple videos, I will not be implementing any code. Like I always say, I'm just going to try to explain the algorithm in English, and that's really the biggest obstacle to solving these problems. So once you understand how to approach the problem and you understand the algorithm in English, then implementing it into code shouldn't be too difficult. So let's take a look at the problem description. So I'm not actually going to read this, I'm just going to paraphrase and give you a gist of what is happening. So our goal, we're given an input list of stones. 0 represents the location that the stone is at. So you have a stone at location 0, a stone at 1, stone at location 3, all the way until a stone at location 17. So as you can see, there's gaps, between 12 and 17. So the gaps represent, just whatever, like those locations are filled with water or something. So, our goal is to be able to get to this from the starting point all the way until the ending stone. And if you can get to the ending stone based on their constraints, which I'll explain in a second, then we return true. If we can't get to the end, then we return false. So what are our constraints for each jump? So we have kind of like an edge case or base case, whatever you call it, where we're always going to have a stone at location 0 and 1. In every case that they will have, behind the scenes, every case will have a stone at location 0 and at location 1, because, we're always starting at the 0th location, and then our first jump must always be 1 unit. So we're always going to have our second stone at location 1. So besides that though, all the other jumps, once we're at location 1, then we can jump either k minus 1, k, or k plus 1 units. And what that means is, if your last jump, it says that if your last jump is labeled as k, so to get from 0 to 1, that jump was size 1, right? So your k value is 1, so then your next jump must either be of size 0, size 1, or size 2. So, if we look at a jump of size 2, that can get us from here to 3. And then from 3, our k value, our previous jump was size k of 2. So then from 3, we can either jump k minus 1, which is 1, or k, which is 2, or k plus 1, which is 3. So we can either jump size 2, or size 3 from this stone here. And so, looks like jump of size 2 works, but actually a jump of size 3 gets us ahead to here, so that works either, right? So now you can see how you might have to use dynamic programming, because we might have to explore multiple paths here. We might actually have to try out the option of taking this route to go to the 5, or we should try the route of going 6. So we have to be able to store both states and explore both possibilities. And so what we're going to do here is, we don't necessarily need to make a DP list, like a conventional DP list, but it is still kind of a DP state transition, because we're going to be using a hash map instead. And what we're going to do is we're going to store all so first of all, the key is going to just be the stone, the location of the stone. As you can see, we have 0, 1, 3, 5, whatever, 17, and then the keys are just matching that. And then the values are going to be sets, and the sets are going to contain all the sizes of the possible jumps to get to that stone. As we saw, for 3, you can use a size k equals 2 jump to go from 1 to 3. So that's why we have 2 in this set. And then, as you can see, for 6, we can get to 6 with a jump of size 3 or with a jump of size 1. This, you can get from 3 to 6, so that's a jump of size 3, or you can go from 5 to 6, which is a jump of size 1. So ultimately, if we have, if this last stone has a value in its set, if the set is empty, that means we can't get to it. But if there's a value in there, that means it doesn't matter what the value is, you know, whether the jump was 2, 4, 5, whatever. If there's a value present in this last stone set, that means we got there somehow. One of the paths was able to get us there. So let's walk through another example where you can't get to the end, and I'm going to just go through this whole example from scratch and show you how I'm going to fill this hash map. And so like I said earlier, you know, you're starting at the 0th location, so you're not taking any jump size to get there. You're just getting plopped down right there at the starting point. So, you know, doesn't really matter what's in this set. It doesn't matter, but you can just pre-fill it to 0. What does matter though is this first stone, location 1. The only possible, this is also another edge case. You know, this is a case where you're not looking at these 3 possible k-1, k+1 options. You're told that you can only get to location 1 with a jump of size 1 from the starting point. So you pre-fill this to 1, and then you can start iterating from this location. So from index 1 is when you can start doing the bulk of the problem, the real computation. So let's look at what we can do for 2, right? So while we're at 1, our k value is 1. You know, we can only get to 1 with a jump size of 1. So then we can do 1. So from our current stone, we can add k-1, which is 0. Or we can do 1 plus 1 plus k, or 1 plus k+1, which is 2. So let's see if 1 plus 0 is in our set. Oh yeah, also this is also another case where you can kind of just ignore. If the jump size is 0, then you know it doesn't. You're just looping back to yourself, so that doesn't really tell us anything. So this case is really negligible. You know, if you include it, it doesn't really make a difference. If you exclude it, you know, it'll make your map cleaner and easier to read. So I'll just discard it. If the jump is size 0, then you can just forget about it. It's not gonna, you know, we're already at this stone. It's not helping us, you know, reach a different stone. So I mean, our end goal is to reach the last stone. So if it's not helping us reach a stone ahead of us, it's not really useful information. So we can get rid of that. So 1 plus 1, right, is 2. So from the first stone, we can use a jump of size 1 to get to 2. Oh, we see that 2 is in our map. 2 is one of the valid stone locations in our map. So we add this jump of size 1, which helps us get to 2. And then we have 1 plus 2 is 3. Is the location 3 in our map? It is. So we can input this jump of size 2 into our set for stone 3. And you can keep going and going. I'm going to continue and just try to walk you through this so you fully understand what's going on. So from 2, right? So once we get to each new stone, all of the possible jump sizes to get to that stone have already been pre-filled. You know, that's this one here is the only jump size that we can take to get to this 2. You know, so once we're here, our set is already filled. This set will not change once we're here. What we can do is use this set to find out which further locations we can get to from our current stone. So we can take the 2 plus, you know, 0 again. So 2, you know, as I told you, if a jump size is 0, it's negligible, so we can forget about that. And then we can do 2 plus 1, and then we can do 2 plus 2, right? So this, like I said, is not useful information. 2 plus 1 is 3. So, you know, is 3 in our map? It is. So we can add this jump size of 1 into our map. And then you see 2 plus 2 is 4. Is 4 in our map? Oh, yes, it is. So we can add this jump size of 2 into our map. Alright, so then we're going to be at index 3. So now we have 2 different jump sizes to get to location 3. So we'll have to do 3 plus 2 minus 0, or 2 minus 1, which is 1. Then we can do 3 plus 2, and then we can do 3 plus 3. And then also, we found the 3 options for k of 2, right? Now when k is 1, we have to find all 3 options for that as well. So 3 plus 0, 3 plus 1, and then 3 plus 2. Right, so like I said, this 0 is kind of useless information. So is 4, 3 plus 1 is 4. Is 4 in the map? Yes, it is. So we can add that jump size of 1 into our map for 4. And then, what's going on? Alright, and then 3 plus 2 is 5. Is 5 a valid stone location? No, it's not. So we don't add that to the map. 3 plus 3 is 6. Is 6 a valid stone location? No, it's not. So we forget about that. So 3 plus 1, again, we have 4. So is 4 in our map? Yes. And so this is a set, right? So if we try to add this jump size of 1 again, you know, it's not going to add to the set because it's already in there. So this just does nothing, but, you know, we don't have to worry about, you know, handling that because we're using a set. So it'll just, you know, I don't know, does it override or something? It just won't add a duplicate 1 to our set. So we're good to go here. And then 3 plus 2 is 5. Is 5 in our a valid stone location? No, it's not. So we continue. Right, so same with 4. We can do the same stuff for 4, right? 4 plus 1. 4 plus 2. And then 4 plus 3. Right, and then you can do 4 plus 0, which I said is useless. So let's just skip to 4 plus 1. And then 4 plus 2. So I'm going to just kind of speed through this. Is 5 a valid stone location? Nope. Is 6 a valid stone location? Nope. Is 7 a valid stone location? Nope. Is 5 a valid stone location? Nope. Is 6 a valid stone location? Nope. So now we're at 8, and we realize we can't even get to 8. We can't get to 8, right? So then, you know, if we wanted to loop through our set, there'd be nothing to loop through. And then eventually, once we finish iterating through all these numbers, you know, there will be nothing in the set for 8, 9, or 11. So we, you know, our final answer should return false because there's no jump size that gets us to stone 11, and, you know, let alone stone 8. All right. So I hope that explanation was good enough to help you guys understand the problem. Like I said, if you go and take what you've learned in this video and try to implement it into code, that'll help you reinforce your learning and really help you understand how to solve this problem, you know, on your own completely without too much hand holding. So yep, hope you guys learned something new. Hope you guys enjoyed. Hopefully you enjoy my teaching style. Hopefully it's effective. If it's not, let me know. I can improve on some things and try to make my videos more useful. So yeah, that's it. Have a nice day.